Hello, in this video I have my helpers Allie and Clara, and we're going to talk about dipole moments, both of individual bonds and of the overall molecule. Can you say hi, Allie?
Hi.
Hi. Can you say hi, Clara?
Hi.
Alright, let's go. Remember from the electronegativity video that we can look at differences in electronegativity between the two atoms involved in a bond and make a classification. If the electronegativity is between 0 and 0.3, 0.4, somewhere in there, we just say this is covalent, or we might use the words nonpolar. Whereas if the electronegativity difference is between around 0.4 and say 2, then we have a polar bond. A covalent bond, but a polar bond. And remember that polar bonds, the electrons spent more time around one atom than the other, and so therefore we had a greater electron density around one of the atoms. So we called it a polar bond before, but here we're calling it a dipole moment, and that is the same thing. A polar bond has a dipole moment by definition. That's what that means. They're effectively two interchangeable words for the same thing. So how do you define a dipole moment? So it gets the symbol mu. This is not a U, it's a Greek letter mu. And if you zoom in on it, it'll look a little something like this. And that is the separation of partial charges. So over here we have the partial positive charge and the partial negative charge from our hydrogen fluoride molecule. So you can define dipole moment with a little math equation here, so that mu is the charge times the distance between the charges. So if the atoms are closer or farther, that would change things. And we typically express this in units of debye, and that is related to some coulombs per meter. Coulomb is the SI unit of charge, and then meter is the distance apart. And I'm sorry, I said coulombs per meter, but since they're not divided, it should have just been coulomb meters. My fault. So you can imagine this as kind of like a tug of war. The hydrogen and the fluorine are tugging over electrons. Since fluorine is stronger, then it wins the tug of war and it has more electrons around it. That makes it a polar bond. That means it has a dipole moment. So who better to demonstrate a tug of war than Sadie the dog? And so if you have an element dogium and an element huminium, who gets more electrons depends on who has a higher electronegativity. So if I have a higher electronegativity, get the rope, then I'm going to pull the electrons more towards me. And if she has a higher electronegativity, then she's going to take the electrons towards her. That's kind of how it works. If I get more of the electrons because I have a higher electronegativity, then I have a partial negative charge, and vice versa if Sadie wins. Did you win? She steals her prize and walks away. So we represent these dipole moments with a special arrow, and this is drawn to represent both the direction and the magnitude of the dipole moment. So you can see it on this picture now, that we have the main arrow here, and then we have a little plus sign on one end of it. And so this symbolizes that this end of it is positive, and then this end of it over here is negative. That's how this is set up. And that, I think, helps make it easier to remember because the left side with the plus on the tail of the arrow is the partial positive side, whereas the right side, the negative side, gets the arrow head. Now, just to make things incredibly confusing, in this class and most other general and organic chemistry textbooks, this is what we do. We do the little plus sign on the positive end and point towards the negative end. However, physicists, the International Union of Pure and Applied Chemistry, which is the organization that makes the standards for chemistry, and your textbook all use this convention. So credit to your textbook for trying to adopt the actual standard for how to draw dipole moments. Just unfortunately, the rest of chemistry doesn't do that. So in this formalism over here, you have the tail of the arrow at the negative end, and you can remember it because it's just a negative tail. It doesn't have a plus in it. It's just the negative end has the tail, and then this points towards the positive end with the partial positive over here. So one of these two formalisms may make more sense to you, and if that's the case, use it and just be consistent about it. I'm going to use the plus at the positive end point towards the negative end convention, just so that you're more prepared for organic chemistry, and because this is what I learned, honestly. And so when you see my stuff, it'll be drawn this way. Now when you go and look in your book, you'll have the other convention, so just keep that in mind. And so if we were to go back to this slide here and draw the other arrow on it, it would point the other direction like this. Okay, so up until now we've discussed dipole moments that are for an individual bond, but you can apply this logic across an entire molecule. And this is the ultimate thing that I think matters more, because whether your molecule is polar or not dramatically affects its behavior, properties, etc. So we can take the same definition for a dipole moment, still has the same sign, mu, and talk about this as separation of partial charges across a whole molecule instead of across a whole bond. So we can use the phrase a polar molecule, the molecule has a net dipole moment, a nonpolar molecule, it does not. And keep in mind, to be polar means that you have a net dipole moment. And the word net here just means summed across the molecule. Okay, so let's talk about polyatomic molecules and their dipole moments. So, the net dipole moment is effectively the vector sum of the individual bond moments. Because remember, each dipole moment from a bond is a vector, so if you just add those up, taking into account both magnitude, so how long the arrow is, which represents the size of the electronegativity difference between the atoms. If you add those arrows up and keep in mind their orientation as they point around, then if you get a resultant arrow, then that means you have a polar molecule, whereas if you do not get a resultant arrow, the molecule is nonpolar. So the examples here, if you have, say, a central atom and then two external atoms out here, and if you add the two arrows up, then you would get no net force because they're pointing with the same magnitude, so the same length, in opposite directions. Whereas if you have something like this, with three atoms here, and you have some polar bonds and they point at different directions that are not straight across from each other, then you'll get a net force on the object. So, in order to figure out whether a molecule is polar or not, you have to look at the geometry of the molecule, how these bonds are actually arranged in space. We tell you how to predict geometry in Chapter 8, but for now we'll just tell you what the geometry is. So for example, we have boron trifluoride, and who better to help me explain this example than my helpers for the day? In this example we have boron trifluoride, which, as we have on the whiteboard over here, is a trigonal planar molecule. So you have the boron, and it's bound to 3 fluorine atoms. And we want to figure out the net dipole moment for this molecule. So each one of these bonds is polar. The electronegativity of the fluorine is 4.0 as definition. The electronegativity of the boron is 2.0. There you go, good helping, Clara. And so each one of these has a dipole moment that goes from the positive boron to the negative fluorine. And drawing it with the arrow with the plus sign, it'll look something like that. Okay, so now all 3 of these bonds have the same polarity within the individual bond. And then we need to figure out what happens to the overall molecule. Do these polar bonds add up, or do they cancel out? And so for that, you need to think of tug-of-war.
Yep, it sure is.
It sure is. All right, so let's play some tug-of-war. So boron trifluoride is a trigonal planar molecule, and while we haven't talked about the names of geometries yet, basically the boron and the 3 fluorine atoms all lie in the same plane. just like they're laying on a floor, which makes it a great, I'm not even in the video, it makes it a great starting point to talk about geometry. Yeah, is it so exciting? Okay, so you can imagine polarity like it's a tug-of-war. So do you want to play tug-of-war, Allie?
Yeah.
Okay, so. All right, so if the strength at which we're pulling represents the polarity of the bond. Oh, hey, come back. So if the strength at which we're pulling represents the polarity of the bond, and if we all pull at equal strengths, which is the case if we are all fluorine atoms, then the boron doesn't go anywhere. Because we're all pulling at equal strengths, and we're pulling at the same intervals around the central atom. You know, we each have a 120-degree angle from each other, and so our forces are going to cancel out. So this would be the case for boron trifluoride, and that would make it a non-polar molecule. I don't even know if my head's in this video. There we go. Okay, so back to this slide that shows the pictures again. Overall, this molecule is non-polar because the polar bonds all cancel out in space, given the geometry of the molecule. So let's make a hypothetical here while Clara plays with a destroyed tissue. Yeah, thank you. And say we took one of the fluorine atoms and replaced it with a bromine. So here's our bromine. Bromine is less electronegative than fluorine, and so it's going to have less of a pull from the boron. So now if we redo our tug-of-war, sometimes you gotta let the kids win. So if, in this example, the boron-fluorine bonds are much more polar, and so therefore they would pull stronger than the boron-bromine bond. So ready, set, go! All right, and the kids are pulling stronger than I am, so the center of the molecule would move in this example, which tells you that there's a net polarity difference across the molecule. So there's a partial positive charge over here by the bromine and a partial negative charge towards the fluorines. Oh, did Allie pull the leash from you? Yeah. So to put this on paper, the electronegativity value of boron is 2, and bromine is about 3, 2.96. So that means this is a polar bond that points towards the bromine. Positive end of this is on boron, so it has a lower electronegativity. But that's overall a smaller difference than between boron and fluorine, which is 2.04 to 3.98. So each one of these arrows is longer, which we use to represent a larger magnitude. So when you add these arrows together, you get an overall net resultant dipole moment that points this way. Okay, in this example, we look at the bond moments and resultant molecular dipole moments for ammonia, NH3, and nitrogen trifluoride. So the geometry of these molecules is called trigonal pyramidal, in that these three atoms that would lie on the plane, if you imagine them sitting on the top of a table, then the nitrogen rises above that plane and makes a little pyramid with a triangular base. Now, each one of these NH bonds on the left is polar, with the positive side pointing towards the hydrogen. And then if you add these up, they will add up to an overall net dipole moment that points up, like this. And so I drew it in teal over the molecule. The little picture that I have here draws it above the molecule. Right. Okay. Now, the kind of opposite case is true if you have nitrogen trifluoride, where the fluorine is more electronegative than the nitrogen. So that means this bond has the positive side towards the nitrogen, and it points out towards the fluorine. And then if you add all of these up, you get a resultant dipole moment that points down. It's still a polar molecule, regardless of which way this dipole moment is. The definition of polar molecule is that it has a net dipole moment, the direction of which doesn't matter for it being a polar molecule. However, I do want you to be able to draw this, to look at each individual bond dipole moment, and then add them up, considering magnitude and orientation, and create a resultant net dipole moment and draw that either on the molecule or you can draw it off to the side if you want. But just somehow be able to say this is, pointing this way. So I think that's a good exercise in looking at these vectors and figuring out how they would all work in space. So this is something I will ask you to do on an exam, is to draw the net dipole moment on a molecule. Now down in the bottom we have electron density maps. And these ones are set up so that the red part is negative and the blue part is positive. So if you look at the NH3 on the left, this part of your molecule is going to be partially positive, this part of your molecule is partially negative. So the partial positive is in blue, the partial negative is in red, and that's how it looks. So, and then for the NF3, well, now it's negative down on the bottom and positive kind of near the top. But complicating things is the lone pair up here. We don't touch on that in this class, but that's why this diagram isn't quite how you might expect. We can ignore that. Okay, so the question I can ask you about this at the moment is which of the following molecules has a dipole moment? And you don't know how to predict geometries yet. That's coming very soon. But until that point, I have to tell you the geometry. So I'll do the first one. So H2O is bent. So the first thing you should do is draw the structure. Might as well draw the Lewis structure, because usually I pair these questions together in some form. So when I drew it to represent a bent geometry, and what we mean by that is that this is not straight, right? That's bent. Now, if you look at this, the electronegativities, each one of these hydrogen-oxygen bonds is polar, and they don't cancel each other out in space, and so there's an overall net dipole moment that points up in this case. So this is a net dipole moment, which makes it a polar molecule. Alright, the carbon dioxide, the Lewis structure looks something like this. Now each one of these carbon-oxygen bonds is polar, but since they point in directly opposite directions from each other, it's like you're doing a tug-of-war and both teams are evenly matched, so therefore you don't go anywhere. So you add this up and there's no net dipole moment, so this is a non-polar molecule. Okay, so I'll have you do the sulfur dioxide and I'll put this up as the pop-up question. Okay, and the last thing I want to say is that formal charge, partial charge, and oxidation state are all different concepts, and so I wanted to draw the distinction between them. Formal charge is assumed to be an integer, and it's the difference between valence electrons and electrons assigned in the Lewis structure. Now the sum of the formal charges gives the charge of the molecule, and you always draw them on the Lewis structures if they're not zero. Now that's different than partial charge, which are slight charges that result from unequal sharing of electrons in polar covalent bonds. So you can imagine the magnitude of a partial charge is less than an integer unit of charge. Granted, formal charge doesn't represent the charge of an electron. It's kind of a bookkeeping method. But generally, alright, partial charges are kind of small, but still very important. And sometimes you'll draw them on the Lewis structures if you're asked, if you're trying to show that aspect of it. And then oxidation state, there's a connection to formal charge that you can make, but we haven't talked about that yet. That comes in the second semester of the course. Alright, that's all we have for now. Thanks for watching. You can say bye-bye.
Bye-bye.
Bye.
Can I have my book back?
Yeah, you can have your book back.